Well, hello everybody. So I'm going to talk about some knot theory today. I'm going to introduce you to what it is, some of the big questions in knot theory, and then if we get far enough, hopefully I can tell you about what I do as well. So what is a knot? Knot, intuitively, it's like, you tie knots in your shoelace. But in mathematics, knots have a very particular definition. Because something like a shoelace, you can always undo. You can always pull both ends to undo it. So what we care about in mathematics are circles, things that are closed loops. And so we like to look at these embeddings of circles. What is an embedding? An embedding is a continuous degenerate map. Okay, what does that mean? Well, let's have a look. To be continuous means that you're not can't have any it has to be a closed loop. You have to take some circle from down here and project it into space without breaking that circle. That's what it means to be continuous. And to be injective means you can't then pass that circle through itself. Like, I get my circle, I twist it around, but I can't, in the end, have a circle intersecting itself, because that's not a knot. Your shoelace doesn't pass through itself. So we want these knots to represent, somewhat real objects. And so a knot is something like this on the right. It's a closed object that doesn't intersect itself. And this is what we work with. This is the basis of knot theory. If we embed multiple circles, so we take two circles, say we take two circles from space, we put it in three-dimensional space, we get a link. They have to obey the same rules. They have to be closed, they can't have loose ends, and they can't pass through themselves. And so we get something like this. And you can embed more and more. Each one of the circles that you embed is called a component. This particular link is quite cool, and it's called a Brownian link, which means that if you cut any one of these links, so like you get a pair of scissors and you go and you cut it, then what happens is all the rest of the links fall apart. And you can try and convince yourself that if you say cut the blue link, you should be able to pull the green one, the orange one, and the pink one out. And you should be able to do that for any of them. That's not a general property. Usually if you have links of 5 or 6 components, whatever, if you cut one, chances are the others will stay together, but that's called a Brownian link. So now we get on to kind of the big questions on knot theory, which is what does it mean for two knots to be equivalent? I have this definition of knots, and now I want to try and characterize when I can transform one knot into another knot. What if all knots are the same? What if I can always take this, embedding a circle, and then transform it into another knot? Or are there multiple different knots? We don't actually know this yet. We haven't, proven that there are families of knots. So I might ask, are these two knots equivalent? Intuitive. What do we think? Yes. Because I can take it, the left-hand one, and I can twist it, and I get a circle, which is exactly what we want. So yes, these two knots are equivalent. But possibly a harder question is, are these two knots equivalent? No. Intuitively, maybe not. And it turns out that yes, these knots are not equivalent, but it can be a little bit difficult to see, and that maybe there's some way that I can bend that left-hand knot, which is called the Tricolourability knot, and get to the right-hand knot, just a simple loop. So we need to determine mathematically that, say, the top two knots are equivalent, that our definitions say, yes, we can twist that left-hand knot into the right-hand knot, and that the bottom two knots are not equivalent, and that we can't somehow take that left-hand knot, twist it up in space, and get the right-hand knot. So we come to this theorem of Reidemeister, and this characterizes everything about knot equivalence. To start, I'll say that a knot diagram is what we've been working with. So a knot diagram are these pictures of knots. They're like two-dimensional objects instead of three-dimensional, but they represent three-dimensional knots. They have crossings in them. And Reidemeister says that two knot diagrams represent equivalent knots, so knots in space that I can twist around to get another knot using only moves that you would do at home with knots, right? You can bend and you can whatever. You can't pass knots through themselves. It says that anything you can do in space, you can do on a knot diagram, characterized by 3 moves. So the first one is called the Reidemeister 1 move, and this says that these should all be very intuitive. have a line, you can introduce a twist in it, which seems intuitive. You agree that, if you take a rope and you can just put a little twist in it, that's a valid move. The second move is called the Reidemeister 2 move, which says that if you have two strands, now you can take one of them and either put it behind one or put it in front of one, which again should be quite intuitive. These are like, things that represent really obvious stuff in space that we need to make formal on a diagram. And the last one is the Reidemeister 3 move, which is a little bit more complicated, but it just says that if you have a crossing in your diagram and you have another strand which sits entirely over the crossing or entirely under the crossing, then you can move it to the other side of the crossing. And the way to remember these moves, not that you have to remember them, but is that the Reidemeister 1 move is concerned with one strand. You take one strand and twist it. The Reidemeister 2 move is two strands, and the Reidemeister 3 move is to do with three strands. So the beautiful thing about this theorem is that it represents anything you can do. So one direction is kind of obvious in that yes, these all seem like legal moves that we can do to it. These all seem like ways that yes, we can manipulate them. But it turns out, and this is the beautiful thing about Reidemeister's theorem, that any way that you can pick this representation of the knot out of the page, manipulate it in space, and put it back down onto the page, can be decomposed entirely into a sequence of these three moves. No others. These are all three moves that you need, which is quite beautiful, because now that says that this 3D object, which is actually quite complex, we can project out to 2D, and we only have to work with three moves. And that's the basis of the knot theorem. So now we can start asking questions. Is this a perfect solution? Can we, before, determine whether two knots are equivalent using this system? If two knots are equivalent, and I can tell you from my high level of seeing these knots and putting these knots into the presentation that these two knots are in fact equivalent. There is some sequence of these Reidemeister moves that I can do to manipulate them and turn them into each other. And this is actually a very particularly interesting example. These two knots are called the Pogo pair. And so these, I think these knots are 10 crossings. It happens that this guy named Olsen, when he was cataloging all of these knots from the ground up, he thought that these two knots were different. It turns out that some lawyer named Pogo was looking through these knots and saw that actually I think these two are equivalent, and he ended up showing that yes, there is a way to transform this left-hand knot into a right-hand knot. It's not obvious, but they are in fact equivalent. And I think this only happened in 1973 or something. So actually a fairly recent discovery that these two knots are equivalent. But then we can also ask things like, is the trefoil knot equivalent to the unknot? So the trefoil knot is this simple tri knot, and the unknot is just the loop. If we claim that that's before they're not equivalent, then we're looking for a sequence of moves to, well, we're saying that there can't exist that sequence of moves to get from the trefoil knot to the unknot. So how do we prove that such a sequence of moves doesn't exist? How do I know that I can't apply sequences of Reidemeister moves to that trefoil knot to eventually get it to the unknot? We're not sure. And we can ask more complex questions. Are these two knots equivalent? How do I know? Well, if they are equivalent, there will be a sequence. But I can try, and I may never find that sequence, even though it may exist. And if it doesn't exist, if the two knots aren't equivalent, how will I know that it doesn't exist? That I won't just keep on searching forever? It turns out, in fact, that actually these two knots are equivalent. There is a way to relax this left-hand knot to get to the unknot. Actually finding that sequence is quite a challenge. And you can ask again, are these two knots equivalent? This knot, I think, has 31 crossings. The last one had 19. And this one is in the heart of it. Actually, yes, it is also equivalent to the unknot. Good luck finding the sequence. And the cool thing about these knots in particular is that actually there are no simplifying Reidemeister moves to start off with. You have to manipulate this knot to make it more complex before it starts relaxing into the unknot. So there's no way to say apply 31 Reidemeister moves just to get to the unknot. It's really hard. You have to So this question is posing to actually be pretty difficult. And in fact is a theorem, well not a theorem, sorry, but as of now, there is no known efficient way, efficient meaning like within any reasonable amount of time that doesn't explode exponentially. There is no efficient way of telling whether two knots are equivalent or not, which is really interesting. Maybe there is a way, but we don't know it yet. We don't have an algorithm to say that yes, these two knots are equivalent, other than just brute forcing it, or there are algorithms I believe that work in exponential time. So you increase the number of crossings by 1, and then the time it takes multiplies by say like 3 or 4 or something. But for any large amount of crossings, this solution is entirely unreasonable. So we need ways of telling whether two knots are equivalent or not using some simple tools. And one way we can do that is with this thing called knot invariance. And the definition of a knot invariant is this thing applied to a knot diagram that is equal for all equivalent diagrams. So to explain exactly what that means, that's saying that if I have a knot in space, or I have a knot diagram, I pick it out of the page, I manipulate it in Kauffman and put it back down onto the page, then all of its knot invariants should remain equal. I want to assign it into this, say, is it a happy knot or a sad knot, such that when I pick it up, manipulate it, and put it back down, it remains a happy knot or a sad knot, whatever it was before. I don't want to have something that says, this is a happy knot here, I pick it up, I manipulate it, and I put it down, and now it's a sad knot. We don't want that. We want things that remain the same. Because what that allows us to do, we know that two knots are equivalent if and only if the diagrams are related by Reidemeister moves. That's saying that a knot invariant is a probability of a knot diagram, which says that if you take the diagram, any equivalent diagram has the same knot invariance. All equivalent knots, right, to a happy knot are also happy. Perhaps there are other knots that are also happy. We're not saying that any happy knot is equivalent to any other happy knot, but what we are saying is that any two equivalent knots will be either both happy or both sad, for example. So yes, this is what I'm saying here. Just because two knots are happy doesn't necessarily mean they're equivalent. Now, let's actually do an invariant. And we're going to look at something called tricolourability. And tricolourability will turn out to be a knot invariant, but it might not be obvious at the start. So a knot diagram is tricolorable if you can take each of the strands. So I'll grab a knot here. Let's try and draw. Oh, let me get this right. This is actually really tough. I think like this. There we go. So this is a turbo knot. A strand in a turbo knot is one of these things that goes around here. Then follows where the line has no breaks. Here's a strand, and here's a strand. That's what a knot diagram is tricolorable. If we can take 3 colors, for example, red, green, and blue, and I need to use at least 2 of these colors to call the diagram. And at each crossing in the diagram, there are 3 strands. There's one strand here, there's another strand there, there's another strand there. I need to either use all the same colors or 3 different colors. So we might ask, is the turbo knot tricolorable? Well, it turns out, yes. Let's try, right? I can color this strand green. And then I can color this. I have to use at least 3 colors. So let's try coloring this strand blue. And then tricolorability says that at each crossing, all the colors need to be different. So this strand necessarily has to be red. And let's check. Is tricolorability satisfied? We've used at least 2 colors. In fact, we've used 3. And at each crossing, we have green, blue, red, green, blue, red, green, blue, red. So yes, the turbo knot is tricolorable. If we take something else like the unknot, well, there's only one way to color it. It's either red, it's green, or it's blue. And tricolorability says that we need to use at least 2 colors. So the unknot is not tricolorable. Is that helpful? Yes, if it's a knot invariant. which it is. And I think we have time to prove some of that. So let's actually go and prove that tricolorability is a non-invariant. And so what we have to do is take our three Reidemeister moves, because Reidemeister moves characterize non-equivalence. Let's prove that tricolorability is preserved under Reidemeister moves. And that says that yes, tricolorability is a non-invariant. Two equivalent knots, which are related by Reidemeister moves, must be either yes, both tricolorable, or both not tricolorable. So let's have a look. The first Reidemeister move is you take a line and you transform that into a loop. And we're going to say that if this is tricolorable, then this is tricolorable, and if this is tricolorable, then this is tricolorable. And that would show up in the first Reidemeister move. So let's assume that, for example, this knot is tricolorable, and remember that this is just one part of a big knot. So, and same thing over here. These are all local moves. So we need to ensure that, say, if this one here is tricolorable, and say that strand is red, then the outgoing and ingoing strands of this, like manipulated knot, are also tricolorable, and also have ingoing and outgoing red strands. Well, yes, it's almost obvious there. I can keep going. And this section of the knot is still tricolorable. So we say that if this knot over here is tricolorable, then if this strand happens to be red, is it still tricolorable over here? Yes, because tricolorability says that, if I go back to the theorem for a second, at each crossing, either all three different colors or all three of the same colors, and yes, we've used red 3 times here, which is good. Vice versa, if this knot is tricolorable, so let's actually do it. So we have some local section of the knot over here, and we want to transform it into this. We want to say that if this is tricolorable, then this is also tricolorable. It turns out that the only way for this to be tricolorable is, if I have this section happens to be red, the only way that this knot can be tricolorable is if this strand is also red. There's no other way to tricolor that knot. So, can I now move from this to this? Well, yes, I can. I just keep it green. And so tricolorability is preserved under at least Reidemeister moves. We need to now do that for the second move. I won't go into the third move. I'll leave it as an exercise for the reader. But let's have a look. So we're going to take 2 strands. Going to, I can see that. Let me going to 1 and go under. Technically, you do have to prove it for the case in which the knot goes over, but you can do that in your own time. It's like a identical proof. Let's assume that this is tricolorable. We have 2 cases. We have this. We have that either the top strand is red and the bottom strand is blue, or whatever, they're just different colors. Or we have the case that they're both the same color. So we need to prove that, yes, when we manipulate it like this, it's still tricolorable. Let's do it. If we move over, we want this strand to be red, and we need this strand to be blue here. I still need this strand. What color does that have to be?
Or green.
Green. It has to, so it can't be, Tricolourability says that we either need to use the same color or all different colors. We've already used red and blue, so this last strand has to be green. And yes, it's still tricolorable. That's satisfied. In the case that they're all the same colors, say red, we need to move it along so that it's still tricolorable. Let's bring this strand here. Bring it up. And what can I call that last strand to make sure that it's still tricolorable?
Red.
Red. And we're done. So that's one direction. You also need to prove that going back, it's still tricolorable. So that if I have a tricolorable knot over here, then it's still tricolorable over here. I won't do that because I think you get the idea. But that's the process. And again, prove for the third Reidemeister move, which you can do. And if you have time at the end, I might do that. But what that shows you is that, okay, yes, Tricolourability is invariant under these three Reidemeister moves, but the Reidemeister moves characterize and not being equivalent. So therefore, if one knot is tricolorable, any equivalent knot is also tricolorable. If one knot is not tricolorable, then any equivalent knot is also not tricolorable. Now, what have we just shown? You might recall that yes, the unknot was not tricolorable, because I can only use one color, but the tricolor knot was. But because tricolorability is not invariant, that means that the unknot and the tricolor knot cannot be equivalent. We have just shown that the tricolor knot, I should make sure it's colored. The tricolor knot, the tricolor knot and the unknot are not equivalent. There is no way for me to manipulate the unknot to get the tricolor knot, which is kind of cool. It's actually maybe a surprising result initially. But, well, I guess unsurprising, in that yes, there are multiple knots. Not every knot is equivalent, which is kind of cool. Tricolourability isn't too useful in that it only splits knots into two families. It says tricolorable or not tricolorable. It doesn't tell you anything else. So we've shown that there are at least two different knots in existence. Intuitively, there should be a lot more. I should be able to draw, some random knot, with some amount of crossings that comes up and goes around, flips around, goes through itself, and joins back up. I think I've drawn a knot. It was there for a knot. Yes. That's probably not equivalent to the unknot or the tricolor knot. I'm not sure because I just drawn it randomly. But all we know is that either yes, we can tricolor or no, we cannot. So let's see if we can do better. This is called the Kauffman bracket. And it's a bit more complex than just a yes or no. And it's going to turn out that the Kauffman bracket is also a knot invariant. And the Kauffman bracket is a polynomial. Where you take, and it's denoted, you take some knot or link and you put these angle brackets around it. And it's defined to satisfy three things. The first thing is that the Kauffman bracket of the unknot, just a simple loop, is 1. It's the polynomial 1. The second thing is that if you have some knot which has a crossing in it, the Kauffman bracket says that if you split that crossing, you smooth it out in one direction and the other direction, then you get this is a recursive relationship. And so what this allows us to do is kind of successively go through the knot, smoothing out all the crossings to see what we end up with. And the last thing is that if we have some extraneous component of the knots, we have a knot over here and an extra loop over here, then that splits up into, you just multiply it by this factor. Where do these numbers come from? You'd have to read Callum's paper for that, because what he does is actually prove that this d equals negative a to the minus 2 minus a to the 2 is what is necessary for this thing to become a knot invariant. But this is a recursive relationship. This allows us to take any knot, smooth it out, and get a polynomial out of it. So that's the theorem. I won't prove this because it is quite hard. But this says that yes, the Kauffman bracket is a knot invariant. But because it's a polynomial, well, that allows us to do a lot more than just say yes, tricolorable, or no, not tricolorable. Now we have this vast family of knots that is, one knot might have a to the 4 plus 7a to the 2 minus a to the minus 4. Well, that's a family in itself. Are many knots going to share the same polynomial? Probably not. So we're splitting up these knots of these vast families now, where we can actually tell almost always whether two knots are equivalent or not, which is really, really powerful. There will still be some cases where yes, we may have two non-equivalent knots that have the same Kauffman bracket, but they will not be rare because there's so much variability in the Kauffman polynomial. We can have different coefficients. We can have different exponents. So this is a really powerful tool. And in fact, it's a conjecture, not yet proven, that if the Kauffman bracket of a knot is 1, then in fact that knot is the unknot. It's just a loop. And that's really powerful because that not only says that, well, we know already because the Kauffman bracket is a knot invariant, that if two knots have the same Kauffman bracket, they must, if two knots are equivalent, then they must have the same Kauffman bracket. But this is saying that if they have the same Kauffman bracket, in the case that the Kauffman bracket is 1, then they are the unknot. It's saying that if you take the Kauffman bracket of some complex knot and you get 1, then there is some way to simplify it down to the unknot, which is extremely powerful. This isn't a proven conjecture, it is conjecture, but it has been checked up to, I believe, 20 crossings. It's also been checked with these things called alternating knots, which is where if you run along your knot and you go over, under, it's also true. But in general, it hasn't been proven yet. And in fact, it's not true for more than one component. If you have a link with, say, two circles locked together, I think there's a link which has 58 crossings in it, which is not just like the unlink to things just apart, that actually has a Kauffman bracket of 1, even though it's not true. So this is a conjecture that only applies to knots with one component. And there's also a two-variable version of the Kauffman polynomial, which I use, but the experimentation is kind of similar, so I won't go into it. It's just a bit more powerful than doing that. So now I'm going to go into what I actually do, what my research is. And it's to do with these things called graph knots. And what's a graph to start off with? A graph is a set of vertices and edges. You have like little points in space, and you connect them with edges, and this is a graph. And what you want to do to get a graph knot is to twist knots around each of the edges. So if you imagine, like on each edge putting it like a helix, then this is what I like to call a graph knot. And I just put one in here. What can we do with this? Well, you remember the Kauffman bracket relationship says that if you have your crossing, you want to smooth it out into this like this vertical part and this horizontal part. So let's see what happens if you actually apply that to this case. I want to apply it to this crossing. I want to smooth this crossing out using the Kauffman bracket relationship. So let's have a look. In the case that we do this vertical smoothing, what happens is we kind of get this disconnect where we have now this like hole in the graph. And in the other case where we have this horizontal smoothing, we kind of get another helix that has just one less crossing. So we've simplified it a bit more. And what we can do, well, for a start, the right-hand graph, the one that has one less twist, this is like, now we can kind of do this recursively down until it has no twists left, which is quite useful. But in the left-hand case, what this kind of represents is that now because this edge has like a disconnect in the knot, we can just get rid of it. And so now we're left with this simple graph. So what this says is that we can actually take these graph knots, use this Kauffman relationship to on the left-hand side get a simpler graph, one that's now lost an edge. And on the right-hand side, get something which has one less twist. So we've reduced our graph knot into this, in terms of a simple graph and a less twisty knot. And if you do that all the way down, you're left with just, you've got a big polynomial in terms of these trivial graphs, and that allows you to compute the Kauffman bracket quite explicitly on these graph knots. And this is what my research is about. And the motivation for this is that these kind of helix things are meant to represent RNA or DNA. So this represents like the wrapping of RNA in biological systems, which do exist. I think the coronavirus has this segment in its chain that is actually what's called a pseudoknot in chemistry, which is where you have like, it's not exactly a knot, but it kind of comes in, does a little twist, and then goes out. So you can kind of pull it apart if you are strong enough and small enough to touch the protein. So there's a paper that I read that said that maybe you can target this part of the coronavirus to unknot it, to try and cut it, such that then the coronavirus is rendered ineffective. It's a stretch, obviously, but you know, one day there could be applications of things like this, where you're smoothing out these knots, and these graph knots help you represent specifically, because they are ultices, biological systems. So yeah, that's what I do. Any questions?
So with the RNA,
yes.
so you've got your RNA helices. So you're saying when you make a graph knot, you would do it for every edge would be a helix?
Yes, every edge would be a helix.
And then
So
would it be one knot, or would you just put individual? Would it be a link?
It does. It's a link in general. It could have one component if the twist is the right number, but in general there will be multiple components. Yes. It just depends on how they're twisted. It's like if you have an even amount of like twists on an edge, you might get like 2 different components matching up around. But in general, the number of components could be anything. You had a question? Yeah.
Yeah. So in your theorem about Reidemeister moods,
yeah,
you said that any manipulation can be decomposed into those 3 moods.
Yes.
Do you have like a high-level explanation for the proof of that?
I don't think I've read an exact proof myself, but I guess the kind of thing to think about is that these Reidemeister moods are very intuitive, would you agree? And they represent kind of any interaction that you can have, like 1 strand, 2 strands, 3 strands. If you can kind of believe that any interaction with 4 strands could be broken down to just like 2 interactions with 3 strands, because all you're working with is a crossing, which inherently has 2 strands and some other strand. If you want to pass, say, 2 crossings over each other, you just take one of the strands, do that first, then take the other one, and do that first, and do that next. So it's kind of like the intuition is that you'll never have more than 3 strands interacting at once. Or like if you have 4 strands, you can break it down to 3 and so on. I think this is a very intuitive theorem, but it is, yes, surprising that you can break it down. But yeah, I hope that makes sense a little bit.
Yeah, that's good. Yeah, and thanks for the talk. That's really nice.
Yeah. Thank you. And yes?
Why is it useful to calculate Kauffman brackets of various RNA knot informations?
Because then it's most likely that if you have different Kauffman brackets, well, sorry, if you have 2 knots or 2 RNA knots that have different Kauffman brackets, you know that you can't transform one to the other. And then it's likely that if you have 2 RNA knots that have the same Kauffman bracket, then you can transform it from one to the other. Not guaranteed, because again, it's not invariant, it's not a knot characteristic, but very likely that you can transform into each other. And so now you can say, for example, take a picture of a knot from like a microscope or something and tell, are these 2 knots the same? You take the projection of the knot, that's what an image is. Compute the Kauffman bracket, do it for, like, say, your other image, and see, are these 2 the same, are these different? So, although I don't work with the kind of biological or chemical applications, there's a lot of like classification of anytime you need to classify whether 2 knots are the same or different. I think I'm competing with the smell of pizza, so I think we'll call it that. And yeah.
Thanks, Callum. For everyone, we have feedback and front, so you can help us go, and we can have some more discussions with you.